What's going on, you guys? So today we're converting a binary number in a linked list to an integer. So if you can think of a linked list, we'll have nodes that represent each binary value. So in this case, 101 linked list will represent 101 in binary, which is 2 to the 0, which is 1, plus 2 to the 2, which is 4. So 4 plus 1 is 5. So in this case, we want to return 5. So yeah, so basically what we have is we have a linked list, and we have to get it into an integer form. We can do that either. There's a couple ways we can do that. We can use libraries, so we can use the power. So we could note the position of all the ones in a linked list. So we could loop through all of the nodes in the linked list and note the position that we found the ones, and then use that to add the correct powers of 2 to a final sum. So using math.pow, we could so while head is not null, we could say if head.val equals 1, we're gonna keep track of that. So we're gonna have a powers of 2 list. So if it's 1, we'll have a variable to keep track of the correct power of 2. So in this or the order that we found it in the linked list. And then we'll use that to convert it to the correct power of 2. Okay, so we're gonna add powers of 2. We'll add digits. And then we will increment digits, and we'll move to the next node in the list. So head equals head.next. Okay, so after we loop through all the values in the linked list, we'll have a list with the powers of, we'll have a list with like the order that we found all the ones, right? So we'll append to powers of 2 whenever we find a 1, and we'll append the order that we saw it. So this will be 0, 0, 1, 2, this will be 3, 4, 5, this will be 6, 7, 8 that we'll append. So we'll have this list. It'll be 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8. And what we want is, how many are there in here? So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 total. Okay, so how do we take, so after this is looped through the whole thing, digits will become, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So digits will equal 15. Okay, so how do we get our correct sum? If we have a list of all the ones occurrences and the total number of digits, so sum will equal, we can do for power in powers of 2, we'll say sum plus equals, and we'll set up a sum variable. And this is all pseudocode as well. Okay. And what are we going to do with sum? We're going to do 2.0 to the power. So 2 raised to digits minus 1 minus power. So in this case, what would this be for this one? So it would be 14, 2 to the 14 plus 2 to the 11 plus 2 to the 8, 2 to the 9, and 2 to the 10. Let's see. So let's do that. So 2 to the 14 plus 2 to the. All right. Let's write this down. Let's write this down here. 2 to the 14 plus 2 to the 14 minus this minus 3 is 11 plus 2 to the 14 minus 6 is 8 plus 2 to the 9 plus 2 to the 10. Okay, so theoretically this should equal 18,880. Copy that. Let's see here. Uh-oh. Okay, what did we do wrong here? Oh, 2 to the 11. Why do we have 2 to the 11? Is that correct? Fourteen minus 0, 14, 14 minus 3, 11, 14 minus 6, 8, 14 minus 7, 7, 7. 14 minus 8 is 6. Okay. This is why we leave the math to the calculators. All right. Let's try this. Okay, there you go, guys. So this is one way to do it if we're using a math, if we're using a library. If we want to use bit operations, so it'll be, if you're familiar with bit operations, it's a little bit simpler. But let's see. So we can use bit operations. And let's think about, let's add time complexity here. So let's see, let's see. So we have to loop through each node in list node. So it's equivalent to the size of the number of nodes in list node. So let's call that O of n. And then afterwards we loop through some subset of n. So it's like 2n or just n. Time complexity and space complexity. So no recursive calls. We are storing this list. So I'm going to call this O of 1 space complexity. Although if you think about it, if we got a really long linked list, like one that couldn't even fit in a computer's memory, well, let's think about it. Yeah, so if we keep adding values to powers of 2, it could eventually fill up all of a computer's memory. So this is like, it's some proportion of n. So I'm going to call this O of n space complexity. It's like n over 100 or something, but as n approaches infinity, that's just O of n space complexity. So bit operations, So if we do 1 and we shift left 1, that will equal 2. And in bit operations, it's going to look like this, right? So 1 shift left 1 equals 0, 1, 0. And so we can use that fact to just grab, so we can grab each value of the head and just shift over and add 1 if necessary. So how do we shift left and add 1? So shift left, it sticks a 0. It sticks a 0 on the right hand side. To add 1, if we do an OR, so 0, 1, 0, bitwise OR with 1. So bitwise OR returns 1 if either value is 1 or if both are 1. So it's going to turn 0, 1, 1. So that's a bitwise OR with 1. So we can shift this left and bitwise OR with 1. And it'll add a 0 on the end, and it'll basically add a 1 on the end, right? So we go from 0, 0, 1 to 0, 1, 1. So it shifts the 1 left, and it adds a 1 at the end. That's what this operation here does. And so let's think about how this will work for some examples. Let's run through 1, 0, 1. Okay? So say we have 1, 0, 1 list node. 1, 0, 1, null, right? So let's say we're going to start with sum equals 0. Okay, so this is what we start with. Okay, so now we're going to pop off the first value, the head value. We're going to say sum is equal to 0 shift left 1 or 1. Okay, so what's 0 shift left 1? It's just 0. So 0 bitwise OR with 1, that equals 1. Okay? All right, let's do the next one. All right, now let's pop off 0. So, okay, so this is our updated value. Oh, and this isn't 1, this is, sorry. So we only want to add 1 when obviously we run into a 1. So in this case it was 1, but in this case it's going to be 0, right? So we're not adding 1 every single time. We may just want to, like if the current value is 0, we just want to shift left 1 bit and not add 1. So in this case, so here we popped off a 1. Here, this is going to be easier. Let's say the current value is 1. Current value is 0, right? And I'll note where we're at right here. So we're right here. So we've shifted 0 to the left and bitwise OR with 1. So we've got 1. This is after the first value. So on the second value, we're shifting our current value to the left 1. And we're bitwising OR with 0. And so this is going to be equal to 0, 1, 0. Okay, so now we're going to shift our current position to 1. So now we want to do this operation with 1. So we'll say sum is equal to 0, 1, 0. We're going to shift it left 1, and we're going to bitwise OR with 1 this time. And this is going to equal, so 0, 1, 0 shifted to the left equals 1, 0, 0. And if we bitwise OR with 1, that equals 1, 0, 1, right? And then we're going to exit out of our loop because we reached null, because x reaches null, and we'll return this value here. And if we return this value here, that's going to equal 5. And so that's how we can use bitwise operations to do the same thing as all these operations in base 10. So this is going to be a little bit less code. Let's write up the pseudocode. Bitwise. Okay, so let's say sum equals 0, while head does not equal no. So we're going to loop through all the values of head of our linked list. We're going to set sum equals to sum shift left 1, and we're going to bitwise OR with head.val. So we're going to add 1 when the current value is 1. We're going to add 0 when the current value is 0, and then we're gonna move head to the next value. Okay. And then once we've gone through every single value in the linked list, we're going to return the sum. You know, if we're doing 5, 1, 0, 1 is going to return 5. Okay, and let's think about space and time complexity. We're going to loop through each value of the linked list, so O of n time complexity, and O of 1 space complexity. So if you think about, let's say there's 1 million values in O of, let's say there's so many values you couldn't fit all of the values in an array in a computer's memory. Well, this one is it's not storing each value, it's just adding it to a sum. It's storing 1 integer value. That's it. So as long as we're not getting an integer overflow, this is going to be able to use less space than the other one here, because in this one we have to store the positions of our powers of 2. So if you think about, we have like a huge amount we have this really long linked list. We might end up getting a powers of 2 array that ends up becoming very long and might not even fit in a computer's memory. But that's not a concern with this one here, because we're not using an array to store powers of 2 indices. So this one's a little bit better. It takes some getting used to, like shifting left and bitwise OR operations. I suggest you go ahead and work this example, just if you do 5 to 10 examples of these, it's going to start making intuitive sense, and it's going to get a lot simpler. So let's do the bitwise operations one. Okay, so we're going to say our var sum equal to 0. We're going to say current is equal to head. And we do this because function input values are read only. So we need a writable value. So we're going to create current. We're going to say while current is not null, we're going to say sum is equal to, we're going to shift sum left 1 bit, and we're going to add 1. We're going to add 1 if it's 1. If it's 0, we're not going to do anything. And we're going to increment current. So this question mark, that's a null safety check for Kotlin. So if current is null, it'll set this whole thing to null, and it will avoid getting a null pointer exception. So when we're done, we're going to return sum. All right. Let's see. Okay, there you go, guys. So that has been, we're using some linked lists, we're using binary operations, combining the two. Convert binary number in a linked list to integer. Stay tuned for the next one, guys. See ya.